Good morning, everyone. Let's get started. So everyone has submitted homework, and you see the new one. How difficult was the last one? Like from 1 to 10, how much is it? 7?
Yeah, I'd agree with that. I'd say a good chunk of the homework was like a 5, and then problem 6 just took a lot of thought.
One difficult one, others are okay. 6.
Yeah, 6 wasn't too bad once you realized the trick, or are told the trick in office hours.
Oh, I think I should release the solution, right? Yeah. I will release it soon, and if you have further questions, you can come to either my office or TA's office hour. And the new one will be due next Tuesday before the class, 9:30 a.m.
And just one quick question about the take-home exam next week. So what lecture does it cover up until?
Covers up to the one before homework 2. So before today's lecture.
It covers homework 2 as well.
Homework 2, yeah, homework 2, yes. Yeah. Yeah. Anything before this lecture, today's lecture. The midterm will be from Tuesday morning 9:30 to Thursday midnight, so 11:55 p.m. on Thursday. So we have 2 days and a half. Okay, today let's talk about a new method. It's still a first-order method using the gradient, but this is a projection-free method. Previously, when we minimize over a set Q, we need to do a projection onto Q, right? But projection sometimes can be difficult for some closed convex set. So the problem we are mainly interested in is still minimize f of x. X is in the set Q, closed convex. The typical algorithm we use is projective gradient. Right. Note here, this is a projection operator. It can be expensive sometimes. So in today's lecture, we want to design an algorithm that is projection-free. We do not do projection anymore. And this is called Frank-Wolfe method. It's also called, also known as the conditional gradient. Conditional gradient method. And this is projection-free. So let's reformulate the projective gradient method. As we have seen before, this is a minimizer of a linearized optimization problem. Okay, so this one and this, they are equivalent to each other. So the reason why we have a projection is because this is a quadratic model. So suppose this is your function f. This is not quadratic function. And at a certain point, xk, this is my current iteration, k. I build a quadratic model. Usually hk is, let's now go to 1 over L. So This is more flattened. It's a lower approximation. This is the model. It's because we build this lower approximation to the function f, and we minimize for this function over the set Q. That's the reason why we have the projection in the end. Because you can reformulate this one as 1 over 2 hk x minus xk x minus xk reformulate it as this one, and hence the argument over Q for this quadratic function is the projection of this point onto Q, right? So that's the reason why you have the projection. So then what is the way to avoid the projection? The reason is because of this quadratic formulation. So what if we remove this quadratic term? We just build a linearization for the model. We just build a linear model. So that's this line here. And this is just LF x xk. So we ignore the quadratic term. What if we just minimize this linear function over Q? And that is equivalent to the Frank-Wolfe method. Because now your x, let's call this point yk. This is an intermediate point. We just minimize over Q for this linear function. And then we let the new point to be this is our previous iterate. By solving this subproblem, we found the new point yk, and taking a combination of the 2 points. Tk is undetermined now, and then we return the next search point, that is xk plus 1. So this is going to be a loop, we just iterate for different case. And pictorially, it looks like this figure here. This is in, the function f is in 2D, x is like x1, x2. This is how the function f of x looks like, and this is our feasible region Q. So for here, Q, we just assume it's a polyhedron. And suppose this is the point x. Through this point, we build a linear approximation, that is this cutting plane here, right? This the yellow one. And so we minimize this linear function over Q. And we find the minimum point. This is the point y. This is like xk. This is yk. This is xk plus 1, right? So this yk is on the boundary. It's a vertex. And through yk and sk, we draw a line between them and then choose one of the points along the line that is going to be the xk plus 1. And next time, you build a linearization through this new point, xk plus 1, and do it again. So this is how the method works. So we formulate This is equal to minimize the linearization because we just ignore the constant term f of xk. And also the inner product term minus inner product gradient f of x and xk. Okay, so one property of the algorithm is projection free. So this is property one, and the second property is sparsity. The solution is going to be sparse. That's why we say it has sparsity, because there's a theorem in convex geometry called Kerr-Theodore theorem. It's saying that for a point x in a convex body Q in Rn, then the point x can be written as the convex combination of n+1 points in Q. And actually, these n+1 points can be shown to be the extreme points. And these are the vertices. So any point that we will encounter in the process of the Frank-Wolfe method can be written as the convex combination of n+1 points, n+1 vertices in the set Q. And also, on the other hand, the algorithm x+1 So if you do this recursive formula, you will see this is 1 minus tk, 1 minus tk minus 1, xk minus 1. Right, so here we have these 2 points. These are all the vertices of the solution. Suppose our Q is a convex, it's a polyhedron, it's a polytope like this. Then any point y should be a vertex, right? So here you can express this one as except this xk+1, all these points are the vertices. And for this one, you can keep the process, and we can write this one as another convex combination between 2 points, and the last point y should always be a vertex. So do this process until the end, so you will have x0, y0, y1, yk minus 1. So xk is a convex combination of all these points, right? Just like what we do here. So suppose the initial point x0 is also a vertex. You begin from any vertex of the convex from the polytope Q. Then xk is the convex combination of all the vertices. So this means that xk can be written as the convex combination of all the vertices that you encounter here. So suppose we do k iterations much smaller than the number and the dimension here, then xk is really sparse in terms of compared with the dimension n. So this is a sparse representation in terms of the vertices. And And also note that in the extreme case, the number of vertices for an n-dimensional polytope can be as large as 2 to the n. But here we only use at most m plus 1 points. So this is already a sparse representation. But here we are using a number k much smaller than n. So this is even sparser, right? And this is a good property because in some cases, you may want the solution to be sparse. Suppose you are minimizing over L1 ball, or you are solving a low rank SDP, semi-definite programming. Then you are looking, the desired solution is a sparse one. So using Frank-Wolfe method is better than other choices. For example, the mirror descent or the accelerated gradient. Those methods will not generate sparse solution, but this one will.
Professor, just one quick question on the theorem. So does that apply to any Q so long as it's convex and compact, I'm guessing? Or does it have to be compact? I would imagine.
It doesn't have to be. I think compactness is not, so the boundiness is not needed.
Oh, okay. So it's, what would if it wasn't bounded, would the points still be extreme in some sense, or?
Suppose this is your Q.
Okay.
Okay, so then in this region, in this bounded, you're right, in this bounded region, the point can be expressed as the combination of the 3 points. But for point here, you need an array in the Q. So array would be, I think it's called extreme ray. Extreme ray is anything in this region. So extend these two are called extreme rays. So anything in this range, any ray from here, right? All these are rays in this Q. They are between the extreme rays. So a point here beyond this region can be expressed as convex combination of all the extreme points plus a ray in this region. That's another representation theorem. Usually there are 2 ways to represent a point in a cone, either an external representation or internal. I think this one is called something called internal representation. As we mentioned before, solving this constraint problem is a special case of solving the convex composite optimization. Suppose you have another composite function h. If you want to minimize f plus h over Rn, that is more general than minimizing f of x over q, because h can be written as the indicator of the set q. So we will analyze the more general Frank-Wolfe method for solving this general problem. And we're going to modify just this step. This is the equivalent way to formulate this step, right? We just put y into the objective function. So in the general case, you just replace this one by h of x. So in general, we solve this subproblem. And now let's replace this by the general one. If we can solve if we can analyze this generalized Frank-Wolfe method, then we can also analyze the Frank-Wolfe. So we assume H is closed and convex, and also domain of H is bounded, it's compact. And we assume F is closed and convex. And also L smooth. Here we also assume domain of H is contained in domain of F. Here the L smooth is general, so the norm can be a general norm, doesn't have to be the L2. This is a dual norm. The optimal solution set X star is empty. Actually, you can derive, you can show the last one holds if the first two hold. The third property of the method is called norm-free. Because here we do not restrict the norm to be L2 norm. And you will see, you can take any norm you want in the analysis. And one thing to mention is that the sparse solution usually comes from combinatorial optimization. For example, if you want to solve, if you want to represent, so the polytope can actually be a polytope to represent the spanning tree of a graph. So you can view each node as a spanning tree. And you want to represent your graph as a convex combination of those spanning trees. Those are like the skeleton, the basis of the graph. And you really want a sparse representation. But the number of spanning trees for an n-node graph, so the node has n nodes, n vertices, and then the number of edges is going to be on the order of n squared. Right? The complete graph is going to be n times n plus 1 over 2, so it's on the order of n squared. And the number of spanning trees is on this order. Yeah, it's right. It's on this order. There's a -2. Let me put it this way. Suppose we have m node. This is a number of node. Number of nodes is this, and number of edges is n, and this is on the order of m squared. And the number of spanning tree so the number of spanning trees in terms of m, in terms of yeah. The number of spanning trees in terms of number of vertices is m to the m minus 2, and in terms of number of edges, it's exponential in square root of n times log n. Log n or yeah, times log n. So this is really a huge number in terms of n. This is almost like exponential, but slightly less than exponential, but it's still larger than polynomial in n. So you do not want to go through all the vertices and try to do a complex combination of a portion of them to represent a graph. You really want a sparse representation. So that's the place where the Wolfe method plays a role, because you can really generate sparse representation. Your graph is actually a complex combination of a few spanning trees, but not a large number of them. And this is really important in many combinatorial optimization problems and also in deep learning. Whenever you have a signal, you want to represent it as the complex combination of a few of the bases that you have, but the number of bases, basic directions could be exponentially large, and you really want a small portion of them to represent your signal, and this gives you a sparse signal, sparse representation. Okay, let's go back to the convergence analysis. So we first need to define a key quantity called Wolfe gap. This is a function from domain of H R, and S of x is defined to be so we have a few properties for S. The first one is S of x is always non-negative. Second one is S of x is equal to 0. If and only if The second property is saying that if s of x is 0, then this means the point, so this is if and only if both directions, then it means 0, so negative gradient f of x belongs to the subdifferential partial h of x. This also means right, and this is equivalent to say that x is a different point of the original problem. So basically here you find the direction, you find the point such that the derivative of the whole thing is 0, the gradient is 0, right? This basically means the first order optimality condition. This is easy to show using just use the definition of s of x. Let's call the sum as 5. So this is a key property of the Frank-Wolfe method. It gives you the one-step relationship between the point x and basically this is your x plus the next search point. Gives a recursive formula between the 2 points. So let's do the proof. We call x plus as the Thomas combination 1 minus t x plus ty. And so the left-hand side is 5x plus. By definition, this is f of x plus h of x plus. And this is less than or equal to right here we just upper bound the f by its linearization plus a quadratic term. This is by the smoothness of f. And this norm can be general. This is a general norm. And because x plus has this form, so let's plug in the x plus. This is f of x minus t times But here we just expand the linearization and plug in the x plus. So we get the expression for these two terms. And here we just replace x plus by its definition. Okay. And now we use the fact that H is convex. Use the convexity of H. The first three terms stay unchanged. Here we just use the fact H is convex, so H of convex combination is less than or equal to the convex combination of the two H. Right, and now let's combine the f of x and h of x. So we have 5x and put everything else together. This is okay. So this is just by the definition. This is s of x. Because s of x is maximization over u, and the maximization can be written as negative minimum of this function here. And this is by using this definition of y. That exactly gives you the y appearance here. This is equal to the s of x. Just a simple calculation. You will see that. So we proved the lemma. Note that here we do not use the convexity of f, right? We only use h is convex. Convexity of f is not used. So far, we haven't specified the subsize rule TK. And here we give three specific subsize rules. The first one is a predetermined subsize rule. So for any iterate index k, we can set tk to be alpha k, which is 2 over k plus 2. And note that this is between 0 and 1, as would be required for the this alpha to be the combination parameter, so it should be between 0 and 1. And the second one is an adaptive rule where we set beta k to be the minimum of the two values. And the third one is an exact minimization or exact line search. Here, just choose the k that minimizes this quantity. Basically, the motivation for the third one is easy to understand. Basically, we are choosing the t such that the left-hand side is minimized. And the second one is beta k is to minimize the right-hand side with respect to t. So build both left-hand side and right-hand side as function of t. The third one minimizes left-hand side. The second one minimizes the right-hand side. We can show that this is actually the minimizer between 0 and 1 that minimizes this function in terms of t. We will give the motivation later on for the first one. To do the convergence analysis, we need another lemma about the function s of x, which is the Wolfe gap. Any questions so far?
So I just have one question, and sorry, you just erased it. So when you said we didn't use the convexity, didn't we use it when we bounded it by the linearization, or we bounded f by the linearization?
No, that one we do this bound. Here we only use smoothness.
Okay, so that applies to non-convex functions?
Yes.
Okay, interesting. Okay, sorry.
Convexity is the other direction, it's this one.
Oh, right.
This direction. And if you have strong convexity, you have mu over 2 here. So smoothness is for the right-hand side, convexity is for the left-hand side. A non-convex function can also satisfy this property as long as it's smooth. And interesting to note is that for a function to be smooth, you can actually have a lower bound. Even though it's non-convex, you can bound this term by negative L. This is the bound for smooth function, because this is actually, it's an absolute value, so you have both directions. When it's smooth, if you check the notes, I think we present this one in terms of the absolute value. This is bounded by L over 2 x plus minus x. So you also have a lower bound. It's a good point. In this lemma, we do not use the convexity of L, but in the next one, we are going to use convexity of L. This is slightly stronger than the first lemma we stated. We said S of x is negative in that lemma. And actually, we have a stronger bond, a tighter one. This is more bounded by 5x minus phi star. So this is obviously non-negative. Okay, so the first two lines are just by definition for f of x, and the definition of y. Y is the argmin of that function, linearization plus h. And because this is the minimum, so this is less than, actually we can skip this line. We can go directly from this line to this line here. Because this is a maximum over all the u, and you can take u to be x star, so this is obviously greater than to this one. This one can be skipped. You can skip this line. And from here to here, we just combine the terms. And from here to here is a place where we use convexity f. Right, and here we just use definition phi is f plus h. Right, this is a simple proof. This is inactive. This is a convergence result. So for any of the three rules we put there, the predefined, the adaptive, and also the exact minimization, the generalized Frank-Wolfe method satisfies the following convergence. For any k greater than or equal to 1, actually it also holds for 0 because this part is infinity. So 5xk minus phi star, the optimality gap, goes to 0 on the order of 1 over k. And here the diameter, the d, capital D, means the diameter of domain of H basically is the distance between any 2 points in domain of H is bounded by d. So this gives the same complexity or convergence rate as the project gradient method. So in terms of rate, this does not improve it. Remember last lecture, the auxiliary gradient method improves the k to k squared. But the benefit here is that we do not use projection. And in the general method, we do not use, like here we do not use proximal mapping. Because here we have only a linearization, not quadratic approximation. So this is not projection, it's not proximal mapping. We're just solving the subproblem. We assume you have the ability to solve the subproblem. In many cases, it is easier to solve this problem than the proximal mapping or the projection. For example, if the Q is a polytope, this is the best case because we are minimizing a linear function over a polytope. And the polytope can be written as ax less than or equal to b, right? And you're minimizing some linear function c transpose x such that ax less than or equal to b. And this is linear programming. Linear programming can be solved by using some simple method, for example, interior point method or active set or simplex. That's easier than solving a projection onto some polytope in many cases. We're going to use this lemma. Note that here, this x and t, they are in general, they hold for, this inequality holds for any x, t, and y, as long as y is computed using this minimization problem. So we can replace the x, the xk, and the t to be tk. And using that lemma, we have phi of 1 minus tk. This tk is undetermined. We haven't specified this tk is any of the three rules there. This is some tk in general. But this xk is the iterate. Since xk is fixed, xk is one iterate, then this y is actually yk. So xk and yk, they are fixed, but tk is free. We can choose any tk we want. This holds for any tk. So in the first case, if we choose the predefined step size, we choose alpha k. So we choose tk to be alpha k. Then we are going to have just replace all the tk by alpha k. The second case, if we choose the adaptive one, we choose tk to be beta k. Because beta k is the arc mean beta k, as we mentioned, beta k is arc mean of the right-hand side. So now let's we first take tk here to be beta k in this inequality. This is simple. We just replace, because here tk is anyone between 0 and 1. So we choose tk to be beta k. We have the first inequality. And the second one, note that beta is the minimizer for this function here. So we can upper bound the right-hand side by replacing beta k with alpha k, right? Because beta minimizes the right-hand side. And for the third case, that's the exact minimization. We take tk to be eta k. The second inequality follows from this one here, right? Everything is with alpha k. We have the second one. And the first one is because eta k minimizes the left-hand side of that inequality. Right? The third one minimizes the left-hand side. So this is less than or equal to the one with alpha. And so in this case, because we take tk to be alpha k, so the left-hand side here is actually phi of xk plus 1. Right, this is the combination. And in this case, because we take t to be beta k, so this is also phi of xk plus 1. For the same reason, the left-hand side here is also phi of xk plus 1. Right, so in any case, we have this inequality, phi of xk plus 1 less than or equal to this right-hand side with alpha k. Right, it holds for any step size you are taking. So we have this one. Here, replace this distance yk minus xk by d because that's the diameter. And now we are going to use the lower bound on sk. Right, remember we showed S of xk is lower bounded by 5xk minus the minimum phi star. This is an upper bound on the optimatic gap. So we have this inequality. And now let's subtract phi star on both sides. So we have phi xk plus 1 minus phi star. Right, we subtract phi star on both sides, we get this inequality. And here, it's an interesting result because view this as this is the optimality gap. So this gives you a recursive formula for the optimality gap. With one step, the optimality gap contracts by this much, by this factor, but it adds this much error. So you can try to analyze this recursive formula to obtain the final result. Phi of xk minus phi star is upper bounded by something in terms k is 1 over k. And this can be shown using by induction. So we first show that when k is 0, for k is 1, so by induction, we first show the induction hypothesis basis. When k is 1, or when k is 0, no, let's prove this. So we want to show phi of xk minus phi star less than equal to 2LD square over k. This is the one we want to show by induction. So the basic case is when k equals 1. When k is 0, this is trivial, right? This is infinity. So we first talk about when the case k is 1. When k is 1, this is when k is 1, we want to show 5x1 minus phi star. So this is actually the case when k is 0 in this inequality, right? So take k to be 0 here. This is phi 0, 5x0. This is 1 minus alpha 0. Here is alpha 0 square. Because when k is 0 here, alpha 0 is 1. So this term doesn't exist. You only have this bound. Alpha k is 1, alpha 0 is 1. So this is just bounded by LD square over 2. And this is, of course, bounded by this bound, right? This is bounded by 2LD square. Because k is 1. Right? So the basic case is true. So now let's assume assume 3 holds for some k greater than or equal to 0. And then let's think about phi xk plus 1 minus phi star. So using this result, this holds for any k. We can always use this result. Because 3 holds for k, we assume it holds for k. So we can upper bound this one by this bound here. Right, so we have 2LD squared over k. And now let's use the formula for alpha k. So this is k over k plus 2. Right, so this is k plus 2. The k cancels, this is k plus 2 squared, k plus 3, 2LD squared. Right, so summing up, we have k plus 3 on the top, and this is bounded by 2LD squared over k plus 1. And this is exactly this bound for the case when k is k plus 1. Right, so we finished the proof by induction. Any questions? So far we know the intuition for this one and this one, but the first one still seems kind of mysterious to us. One quick answer for this one is, that's my understanding. I don't know how people came up with this step size rule, but from my understanding, this is inspired by the accelerated gradient method we talked last time. I think we don't have enough time to go through the proof to show why this follows from the accelerated gradient method. I will do that next time. But to give you a quick answer, from the algorithm construction, you can see many connections between the two methods. So the claim is Wolfe method is similar to the accelerated composite gradient method with the AT rule. Remember we mentioned 3 rules last time: the Fisher rule, AT rule, and LLM rule. So this similar to the second one, the AT rule. The 2 key steps in the algorithm in accelerated gradient with AT rule is right. If we remove, because in the Wolfe method we do not use quadratic approximation, so let's remove this term. And after removing this one, because our method only has 2 iterate x and y, so we do not have the convex combination x tilde. So let's make this to be x. And this is exactly the first step we do, right? Minimize a linear function plus h over the over Rn, right? This x is in Rn. So this gives the first step in Frank-Wolfe method. And second step is exactly the same. So what we do in Frank-Wolfe is we do a combination of 2 points. One is the iterator you had before. This is like xk we had before in Frank-Wolfe. Here we just change the notation to be y. And the next point, the other point is the latest point you solve in a subproblem, right? So this is xk plus 1 is like the yk in Frank-Wolfe. So if you just do this small change here, then the two method becomes the same, right? And we will show that this analysis of convergence for Frank-Wolfe method, especially using the first step as rule, can be shown in the similar way as what we showed for the convergence of the auxiliary gradient method for with the AT rule. And that explains why alpha k has this order. Basically, the alpha k can be viewed as ak over ak plus 1. This is a notation in auxiliary gradient method. This is a notation in Frank-Wolfe method. And you can show that this is on the order of 2 over k plus 2. And here we just take the one on the boundary 2 over k plus 2. That's the short answer. We will do the convergence analysis in a different way next time.
This is easier. This is the stuff right here. Oh, I'm sorry. Three class. I might have all, yeah, I might have all my classes together. So the 2 credit one.
Wait,
Are you not in a 2 credit one? If so, you, yeah.